The noise outside is an air show, part of the Canadian National Exhibition, the last 2 weeks of August. So if you are here over the weekend, I think you could see it there. It is repeating a couple of times.
Hi.
Did you upload your slides?
So P Rembold. I have it directly on Google, so you should be open.
Oh,
You should
sure.
open
We
it
can just
here.
open it then.
Yeah.
So,
And you're okay with this being recorded?
Yes.
Okay. Here's your pointer. Big button moves forward, bottom one moves backwards, and if you hold down the top one, you get your pointer.
Perfect. Thank you.
so okay, Phila Rembold, please. She will tell us about the role of bases.
Thank you. Am I audible? Yeah. No. Is that better? Fantastic. Thank you. Okay, so it's the second to last session, so I'm taking it in a chill tempo, and I'm going to give another introduction to quantum optimal control, because all good things are four, I guess. Because today I'll be talking about the role of basis functions in quantum optimal control. And to do so, I'll first give a bit of an introduction of what I mean by that before continuing on to some example problems, why you might want to care about that, and then I'll tell you what we found. So, well, quantum optimal control basically solves the problem it tries to solve is whenever you go from a quantum operation to a real quantum system. Huh? Sorry. Sorry. Oh, hi. Whenever you go from a quantum operation to a real quantum system, typically fields are applied to that system to implement that operation, like the pi pulse here. And that's done with some time-dependent control, which is often switch it on and then switch it off again when it's done. However, quantum technology is often more complex than we imagine, so sometimes these don't work quite so well, because there's other effects in the system that we might not consider, like extra energy levels or noise effects. And we can determine how good or bad our controls were by calculating a figure of merit. And in quantum optimal control, we make up these time-dependent pulses in order to improve that figure of merit and find a better way of implementing it. Now, specifically, usually we would use classical optimal control to do that. So the figure of merit from the pulse is passed on to an updating algorithm, which then spits out a new control pulse that's tried again, and so on and so on. So let's have a look at what happens on that classical control side. So the figure of merit is passed on to an updating algorithm, like one that basically takes in the old parameters and then determines a new set of parameters to try to find the best place in the landscape. The landscape here always describes on the z-axis the figure of merit and on x and y the parameters, to find the best place in the landscape where the local optimum is. Then it passes on a new set of parameters. But so far, we've only been talking about pulses. So to go from one to the other, we need some type of parameterization. And the most common one is probably the piecewise constant basis. So I call it a basis here. This is somehow the convention that I choose. Sometimes people rather refer to it just to the way they look at the evolution of the system. Anyway, so for the piecewise constant basis, that would be chopping up our control parts into many little pieces, and then each parameter is for each of these piecewise constant parts. And the algorithms that Ronnie and also Christiane were talking about typically use this type of parameterization. So, but one could also do it another way. For example, with the Fourier basis. So here, this is then sometimes called the chopped random basis algorithms. And specifically, we refer to them as chopped random bases if we want to go to kind of a lower parameter space where we are not exploring a landscape that's quite so high dimensional. So we could choose a few frequencies and then make the phase of these components and the amplitudes the parameters, right? But we could also think of other bases. So for example, like little time steps, and choose a place where to put this time step, and then the parameter to optimize is the amplitude. Okay. However, if I make this so low dimensional and I do an optimization, so I find my way through the parameter landscape, then I might actually see that this isn't optimal. And the place that I've gotten to isn't really where I know that I can go. So one way to kind of get around that without over parameterizing is to say, let's put another bunch of basis elements on this. So if I had 3 frequencies I was optimizing before, I take another 3 and put them on the pulse. And that's then the dressed crab or decrab algorithm. And I can go again from there and maybe find a better optimum. So what I want to talk about today is these kinds of algorithms, and they are useful when you want few parameters and you don't have a very good model or a very complicated model of your system. Because they use kind of a small amount of parameters, but you can also do these optimizations with gradient-free updating algorithms. And they're especially useful in a closed loop application. And by that I mean when the optimization algorithm is directly attached to the experiment rather than running with all of the information you would get through a model. So to motivate why you should care about basis functions, I'll introduce an example of an optimization that we did and tell you how it helped us there to think about these things. And our example is magnetometry with NV centers. This is a much simpler version of the things that were already spoken about in this conference. But to make them clear, I just want to introduce what exactly the NV center does here. So NVs are nitrogen vacancy defects in diamonds. So 2 of the carbons are kicked out, 1 extra nitrogen is in, plus an extra electron. And then these systems are spin 1. So they have the spin 0 and spin 1 level. And if I shine a laser at them, I can initialize them in 0. And if they are in the 0 level, then they are quite bright. And if they're in the 1 level, they are more dim. So they emit this fluorescence. And if I now shine a microwave on them that has this transition frequency between 0 and 1, and I kind of vary that in time, then I can see that the fluorescence will get dimmer exactly at the transition, right? Now, the nice thing, I was talking about magnetometry, the nice thing is that if I apply a constant magnetic field here along the NV center axis, then I actually split up these plus minus 1 levels, and I also split up the dips in my spectrum that I've recorded with my microwave. So with that, one can do magnetometry. With that, we can basically find out how strong the magnetic field is that was applied. Okay, and that's what we wanted to do, but with single NV centers, and NV centers that are very close to the surface of the diamond. It's very hard to fabricate these things because you have all of this noise that comes from the surface, from the bonds there, or you have to do very complicated things in order to make the surface look nicer. So what we cared about specifically was to think about a protocol that would also work for an NV center in the tip of a diamond needle that one can then use to kind of scan over, for example, the surface of a material to map the magnetic field there. And somewhere would be the microwave source. Now, the problem is we want to do good measurements everywhere on the surface, independent on whether we are close to this microwave source or further away. So to do that, we need robustness against drive strength errors. You can imagine closer to the microwave, stronger drive, further away, less drive. Okay. So here is what we wanted to go for. Let me briefly explain this plot. So the x-axis is the drive frequency. So that's the same as the fluorescence I showed before on the x-axis. And then on the y-axis, we have the drive strength. And ideally, we would like a pulse which gives us like robustness against drive strength. So no matter whether it's closer or further away, it's always good. And it should be selective for frequency. We don't want something broad, otherwise we can't really pinpoint which frequency we have here. And in order to optimize this, we modulate the X and Y components of this microwave drive. So this work was done during my PhD with Nimba Oshnik and Elkenor Roofing, you can see here. And this first pulse is a square pulse, so that's what you would typically do, switch it on and off again. And we can see that it's not quite so robust as the optimized pulse, which has a black region that extends further. Unfortunately, the optimized pulse also had this weird sideband here, which we didn't really want because we really wanted something that determines exactly where to go. And so we were looking at why that is, and we saw that it is most likely because of the type of basis function that we were using, which generated pulses that had kind of a bit of more of a wild spectrum. So then we chose something that had more of a more narrow spectrum. And indeed with that, with the sigmoid basis exactly, we could find pulses that were even better. So they were more robust and they were more selective. And with that, indeed, we were able to kind of get our sensitivity, which you can see here, more robust. So you see that this green line extends further in this region than the blue line. And what I haven't told you about is that we also did some other optimization. So all in all, we got quite a bit extra in terms of robustness of our sensitivity. So we were quite happy here. Other reasons for caring about basis functions can also be found for Rydberg atoms, which I think fits quite well here. So this is not my work. This is work from Alice Pagano, who I worked with on the things I will tell you about in a second. So they were looking at moving Rydberg atoms in from one lattice site to another, and so I don't have to tell you more about that because you've already seen it. The typical ansatz that at least their collaborators were using was a piecewise quadratic one in order to get the atom from one place to the other. And they did some simulations to look at finite temperatures, and they tried some different bases, and they saw that if instead of this piecewise quadratic ones, they used sinc functions, they were able to get nicer results when optimizing. Okay, so now I hope you believe me that you should care about basis functions. So I'll tell you what we looked at. So this work was done with Simone Montangero and Tommaso Calaco, just as and Matthias Müller, just as well as the Envy Center staff, and with Alice Pagano. So in general, if you think about how many basis elements you want to choose, you should think about the complexity of the problem, right? If you have too few elements to solve it, then you can't. About the kind of updating algorithm you're using, because some can take more parameters, some fewer, and the computational efficiency. And often it's a good idea to over-parameterize, because then you have a high potential to find a good solution, but you also tend to need a few more function evaluations. And for our closed loop optimizations here, this isn't really an option. So we try to reduce the number of parameters as well as possible. So what we want to avoid is kind of non-contributing parameters. So if I have my pulse here and I want to flip my qubit, then applying something that is faster than the timescale of the system won't help me. Similarly, if I'm trying to kind of optimize the integral of this pulse for some reason, using a basis function that doesn't change that integral is also useless. So we try to avoid these kinds of things. And in order to have a few bases for comparison, we chose 3 of them. one could do many more. Yeah, I mean, this is really not exhaustive. We really just wanted to see how much of a difference basis functions can make. So the first one is the Fourier basis. So here, as I said in the beginning, like we pick a number of frequencies, optimize the amplitudes of the sine and cosine component, and then in the next time we choose other frequencies, put them on top. Then there's the sinc basis. So here we have these sinc-shaped little like wave packets, basically. We optimize the amplitudes and we pick certain times where we put them and then optimize this. And the cool thing about the sinc function is that they have a fixed bandwidth. So often we are bandwidth limited. So this is kind of very natural. And then the third one is the sigmoid basis. So here we use these time steps that I was talking about before. So in this case, we have a spectrum that's also more narrow, and we pick times and then optimize the amplitudes. It's also somehow a bit of a randomized version of the piecewise constant basis that has been shown to be super effective in many different scenarios, but it's smooth and randomized. So some similarities, some differences. And we did all of this with our little framework that we set up, but you can't see the logo. It's called QCS. You can look over there, then you see it. So this is available on GitHub, and it's pip installable. So the first thing we looked at is quite common problem. So here, as I was briefly mentioning in the beginning, you have 3 levels instead of 2. And the third one is frequency detuned. This is a problem you especially encounter with superconducting qubits. So if you now want to apply a pulse between 0 and 1, then because and you just switch it on and off again, your resonance, then you'll see that actually your spectrum has some contributions at the frequency you want to avoid. And so you get population in the third state where you wouldn't want to go. So you can do other things, like, for example, applying a Gaussian pulse, which makes this a little bit better, but doesn't quite solve the problem either. And then there's other solutions like drag, for example, derivative removal by adiabatic. I don't know what the G stands for anymore. But it's been shown that optimal control can really solve this problem very efficiently. So we used this and looked at our 3 different bases for it. So in this graph here, the x-axis tells you about the number of function evaluations, so we want to keep that low. And the y-axis tells you about the infidelity, so we also want to keep that low. Actually, this is gate infidelity, right? And then in yellow, there is the sigmoid basis, in green is sinc, and in blue is the Fourier basis. And you can see that here, clearly one does better than the other ones. And actually, the Fourier basis especially has this super broad shaded area around it, which basically describes the potential optimizations you had here. Oh, I should have told you. For each of those, we did like, I think, 10,000 optimizations. And so the solid line for each of them is the median of these optimizations, and then the shaded area describes where kind of the one surrounding it goes. So we can see that for the Fourier basis, if you do 100 optimizations, some of them might converge and some of them might go somewhere totally different. So you can't really know. But for the sigmoid basis, you have the very high probability of converging within a brief time. And that's shown kind of by the top part here. So this tells you when these optimizations manage to get to this black line here, which we've set as a pretty arbitrary kind of convergence criterion. And then the one on the right, I tell you this because I'm going to show you a few more of these plots. The one on the right shows you where they end up. So at the bottom, you can see all of the yellow population. So all of them converge to the minimum we set for the sigmoid basis, and the other ones are a bit further up. So here we can clearly say that the convergence period, so the time they take to converge, is lowest for sigmoid and highest for Fourier basis, and somewhere in between for sinc. And there's more than a factor of 10 between them. So here it really makes sense to pick a basis that works well for the problem. And we also see that the probability of convergence with our 20,000 time steps, 25, differs quite a bit. Okay, so why is that? We can interpret this a bit if we look at the average solutions produced by our optimizations. So here on the right-hand side, you see the sigmoid and basis solution. So we took all the ones that converged and then took the average of those. And on the bottom, I'm going to go to the side a bit. On the bottom, you can see the spectrum, and you see that there is, no spoilers. Okay, haha. On the bottom, you can see that there is this 0 point, and that's actually this difference to the third frequency, to the third level, right? So you see that they all find solutions in order to make sure there's no amplitude there. But somehow, if you look at the sigmoid-based solutions, they look much more similar to each other. They actually also look quite similar to the half analytic solutions that we know here, while the sinc and Fourier bases obviously explore a much larger solution space here, where they find like local optima, but somehow it seems like it's more difficult for them to find the features that are important for this pulse, and they explore regions that are not super useful. Okay, and so we looked at the second problem, which is this Ising chain. So here we have a Hamiltonian. So each of these qubits here has a randomized X and Z component in the Hamiltonian, and then the control is the global ZZ coupling. We randomly choose how strong the X and Z contributions are. So we did this for 2 qubits, and here we see a completely different ranking of our bases. So the sinc basis does really well, and the sigmoid basis is not so great. Actually, if we look at 3 qubits, the sinc basis is even worse, and the sigmoid basis is even worse, and the sinc basis is even better. So we can see that the choice of our basis is obviously quite dependent on the problem. And we also confirmed this and got the same ranking with something that is gradient based. So here we use some automatic differentiations in order to kind of get gradients, which means that we make everything a lot faster. Look here on the left, there's 1,000 function evaluations in total, and here there's 2,000, and it doesn't get quite so good so quickly. So this is much more efficient if you have a good model for your system. But just to say, this doesn't just depend on the algorithm and the way that your updating algorithm works. At least that's how it seems to us, but this is really dependent on the problem. And so we kind of drew 2 conclusions from that. So if you want to choose a good basis for your optimization, maybe look first at a lower dimensional version of the problem, see what a good basis is there, and then try that for the higher one. And the second part is decompose known solutions. So if you know that there are certain features that you need in your pulses, then having bases that can describe them well and efficiently will probably help you to have a faster convergence. Right. So there's many open questions. So of course we want to kind of test this with other problems as well and make this more rigorous, right? We showed some examples now, but it would be really interesting to have a more general answer to these questions. And that's the question, would it help to combine different bases? Or would that maybe be a solution to find a good basis while you're optimizing? As many other bases that would make a lot of sense to test, like Walsh and wavelet bases and all of these. And yeah, then there is, of course, the question whether this still makes any kind of difference once you over-parameterize. Okay, so I've told you about what quantum optimal control means, at least in my definition. I've told you about the role of basis that we found and some example problems. Thank you for your attention.
Very much.